Good morning, everybody. I'm Eli Eikefjord, and it's my big pleasure to welcome you all to this hybrid Presimal MMIV seminar, to both the physical attendees and to those attending online today. So we have two excellent speakers today visiting us from Oslo University Hospital and the Computational Radiology and AI Research Group, CRAI, and that is Caroline Skogen and Atle Bjørnerud. But before introducing them, I would like to introduce you shortly to the Presimal network. So, Okay, so Presimal is a national network for precision imaging and machine learning, and has hospital and university partners from all the health authorities or all health regions in Norway. The network is funded by NSG, Nasjonal Samarbeidsgruppe for Helseforskning i Spesialisthelsetjenesten, and is led and coordinated by MMIV. And Presimal aims to support researchers doing projects on AI in medical imaging across disciplines and across imaging modalities. And we do this by connecting AI researchers in medical imaging. And we do this by sharing and foster interdisciplinary competence and stimulate the exchange of imaging data and methods and infrastructure in medical AI. And we also aim to motivate AI researchers in medical imaging through network activities, such as seminars like this, workshops, conferences, exchange of researchers, and competitions. I'm very pleased also to announce that we are arranging the 4th research school this year, this October, just in Oscarsborg Hotel, just outside Oslo, in Drøbak. And I would like you all to note that the registration for this research school is open now. So we hope to see many of you there, both you in this room and those attending online on this seminar. And please also note that you can also apply for travel grants to Presimal to visit relevant collaboration partners that could be valuable for your AI research. And please go in and see our website, presimal.no, for more information about this. This is just to show you some glimpses of the previous research schools. And we have had many attendees on these schools, in total 130 AI researchers. And they have been attending keynote lectures, poster and oral sessions, networking activities, of course. And we have had image challenges and competitions and panel discussions. But for today, so I hope this can motivate you to attend the October autumn school outside Oslo. So, but today, it's my really big pleasure now introducing you to the two speakers of this seminar today. And the first speaker is Atle Bjørnerud, is here on the image, and many of you, I guess, know him really well. And Atle is a professor, has a background in biophysics and computer science, and he has more than 25 years of experience in medical imaging research and software development. And he's also currently the head of the Radiology and AI Research Group at Oslo University Hospital. And just to briefly introduce also the next speaker after, it's Caroline Skogen. And Caroline, she's a neuroradiologist at Ullevål, Oslo University Hospital, and she also holds a position at CRAI together with Atle. I think it's a 50% position, right, as a senior researcher there. And we look really much forward to hearing about your presentations and your experiences. And first of all, Atle, your experiences running radiology AI lab and the ups and downs sides of that. So welcome to you.
Okay, Thank you very much. Nice introduction. Thanks for the invite. As I said, I had to get up really early today, so I hope I can make sense. So this was the title of my talk. And when I started to look at what I was going to talk about, I noticed that I actually gave a very similar talk to Personal quite recently. So, oh shit, have I done anything since 2023? Have I had anything new to say at all? Or do I just have to use the same old slides? So I will try to, probably some of you have seen some of my slides before. It takes a long time to develop stuff. And it's not so easy to come up with new results all the time. But I think I will just spend some time going through sort of the history of our lab and where we are today. So we started in 2019. My boss had been to a conference, said, okay, AI is coming to take us. We have to get involved in this. Atle, you do that. You get on it. So we had to find a place to be. So we found these old daycare houses that were abandoned that were against the campus. And we said, okay, we can have these ones. They were, of course, completely impractical for any type of office activity. And the hospital didn't have any money, so we had to start ourselves. So we spent like the first few months, getting people in and starting to redecorate and tear down walls and stuff. So that's part of being a scientist. You have to do everything. So that took some time. It was like full of rot and mold, and the walls is terrible. Ants infected and stuff. But it turned out well, and we made a kind of a small garden and started to be self-sufficient with herbs and stuff. But this doesn't make AI, so this was like just groundwork. You may notice Inge Rasmussen Grote here. So he was my kind of partner in crime for the start. It was just the two of us. I think we were just hired because of our initials made sense in terms of upending the AI. But it didn't sort of make us experts in AI. So I think we felt a bit like this to begin with. This was at the time of the pandemic, so I spent a lot of time sitting at home trying to do online courses in AI, and I realized, I'm too old for this. This is going too fast. We have to get the proper people on board, and we have to have a strategy. And so we made a strategy for how we thought we needed to, set ourselves up to make any kind of impact into this new field. And we realized that there are kind of lots of aspects to establishing AI as a kind of lab, in a sense. And there are kind of areas here that are not kind of very common in a hospital, especially software engineering and data engineering. These parts, we're good at research, but we're not really good at making things work in a clinical reality. So we tried to establish, what do we have to do in the different fields to make, to actually make this work. So we kind of split it up. This was very ambitious, and we kind of overlap between the different areas. But the bottom line is that we realized we need proper software engineers. We need actually engineers that can program properly, not just program as a researcher. You have to have people that know what an MLOps is, how you set up proper machine learning operations, how you do version control. So that was like a whole new field to us, and I think for most of the hospital as well. That said, we started to build this, and we started to try to hire. We didn't have much money, but we started to apply for money, and we built up like a fairly good team of people. And we became more like a research hub. So we kind of spread the word that anybody in the hospital that had activities that kind of were related to AI could have a seat in our buildings, and they could come and hang out with the rest of the group. The nice thing about the kindergarten, it's like it has a kitchen. You can sleep there if you want. Actually, some people moved in and slept there, and we were told that's not allowed. We started hanging out there washing and stuff. And said, this is not good. And here we are. So today, I guess we have a fairly broad range of research activities. We have still quite a strong focus on brain because that's kind of our background history. Brain and cancer has always been our main focus, and we kind of continued with that into the AI field. Some work also outside the brain, but we like to keep it high up in the body. So that was sort of where we are today. And I'm always confronted with this by our boss. When are we going to start saving money? Why do we do all this research? We have now a lot of commercial AI solutions. Last time I counted, it's about 250 AI solutions in radiology in Europe. And in the US, it's more than 1,000. And 75% of all AI medical solutions are in radiology. Why don't we just buy this stuff and make it work? So I'll come back to this, but I think you all probably know this, but I have to justify our existence all the time that we cannot just rely on commercial AI solutions. We need, as a big university hospital, to have in-house research. And I think getting people like Caroline on board has really also made this clear to us that the commercial solutions are good, but they're really narrow. It's narrow AI, and they're not always optimized for our purpose. So I've just mentioned some obvious points there. Commercial solutions are also very expensive. We tend to forget it. It can easily be millions per year running a few commercial AI solutions. And they're not kind of they're static in their nature. So we realized that when we want to address specific research questions, and we have a lot of requests for this, we have this specific problem. Can you do something to address this this clinical indication of this pathology? We can retrain models and fine-tune them to local data. I think this, Karin will probably come back to this, but I think this is a very important point if we have the tools to do it. And of course, we need to have in-house knowledge to critically assess this whole field, because there is so much hype in AI that we have to be able to critically assess all the different claims and the methods. And I think it's also, of course, makes it better for sharing applications among research collaborators, national and international. So, we've probably seen this before. So these are kind of the main areas. I think we probably have other areas, but that we focused on. The low-hanging fruit is, of course, segmentation. It's kind of sounds trivial, but it's very important radiology, and it's where convolutional neural networks really have an advantage. They're really good at detecting abnormalities and trained to detect these and segment them. Or classification, where you're not so interested in annotating of pixel by pixel the pathology, but is there pathology, yes, no, and maybe subtypes of pathology. What type of bleed is it? What type of tumor is it? And maybe to put a box around the likely area of pathology. So those two are, of course, connected. The area that we move more into now is prediction, to have generative models to kind of predict future outcomes or predict disease progression, or to generate new types of information from existing information. So I think this is kind of the holy grail maybe of AI moving forward, that you can generate very realistic future probabilities of where a certain process will go. So there is also then an increasing demand for both data and compute power as you move down this axis. But these are at least the areas that we are focusing on mainly. I will not go into detail about all the different projects. I don't have time for that. But we have this project that Karin will talk about, that probably we have spent most time on, getting into a kind of preclinical or early clinical testing, also comparing to commercial solutions. We have a lot of brain tumor projects, both in pediatric brain tumors and in adult tumors, also combining radiomics and these predictive models to predict progression at an early stage. Like most people, we have a lot of activities in Alzheimer's prediction and these type of generative models, which I think is really exciting, and is one of the areas that where I get blown away when I see these results, how clever people like Brian and our labs can create these stable diffusion models where you can create synthetic data, which is extremely similar to the real future data. and also including probability uncertainty maps of the likelihood of the future prediction being correct. So this is very exciting stuff. I think we will see a lot more of this. So some of the challenges then in developing in-house solutions. This is probably also very familiar to you. Data access, it's something we spend a lot of time on. It's supposed to be easy. It's not. It takes a lot of time, a lot of resources, a lot of money. PACS is great for storing data, but it's not a great place to train AI models. You have to get the data out. And we have fairly good control in our own hospital, but when we have collaborating hospitals in Norway, it can take like 9 months to get data out of the system. It's terrible. And it's a real break for how fast we can train models and progress in science. Data curation and QA, also to get not just the data out, but to make it into a format that's usable for AI. It's also a huge, it's a very time-consuming and demanding process because, as you all know, you can't just put random data into your model and hope that it will work. So this is also very time-consuming. Annotation, of course, we rely on people like Herline. They're really good at it, but there are not that many of them, and they don't have a lot of time. So data annotation is also a big challenge. And we would like to have more self-supervised models, but for the time being, most of the time we need some domain experts to at least annotate a certain amount of data. And we also ideally want to link data from multiple sources. We can't just rely on imaging data. We have to combine it with clinical information, which is usually stored in a completely different system with different access rights. And to get all this tied together is challenging, to say the least. When it comes to the deployment part, we have to have a platform that can handle deployment and user interaction. I will come back to this because this is what we spend a lot of time on in our lab. We have to have an evaluation tool for model performance. We have to know over time how well the model performs, both initially and as the model becomes mature and maybe changes over time. We have to have this feedback loop from end user to software developers. Now I'm talking specifically about in-house developed stuff. And this is one of the great advantages of in-house development, that we have this tight interaction between the people actually making the software tools and those using them. And there, of course, this big elephant in the room, regulatory approval. Can we even use in-house developed tools? We have actually now hired a full-time regulatory person just to work on this. And she's actually started yesterday, so it's a bit early, but I think there are more opportunities than we think. So I think this is really exciting. So this is the kind of areas that I will focus a little bit about now, the last part, how we have realized that this is the main hurdles that we have to address to get this, not just as research tools, but making them available at least for some early clinical testing. So that's why we started developing this Neometris platform about 3 years ago. That's one of the first things we did. We hired Jon Nesvold, which is kind of a real clever guy in terms of proper software engineering and machine learning operations. We have a fairly good team of hardcore software developers or platform developers, both front-end and back-end, and what I now have learned, the full stack developers, those that can do everything. So we have developed this platform, which we call an end-to-end solution for development, deployment, and testing of regulator-based solutions, and also to make reports. So that's what we have spent a lot of time and resources on, and I've always been told by my bosses, what do you do, Angela? What is this thing? Why do we spend so much resources on this? And I've had a difficult time answering because it has taken a long time to get the product into something that's actually useful. So now we have this platform, which is integrated into the hospital infrastructure, and we can now deploy our own models at a very kind of easy interface, easy in brackets, it's not easy for everyone, but it's a very standardized interface. So any researcher with a good AI model can come to us and have the model integrated into this workflow. So the brain bleed model, which Karin will talk about, is the one that we have worked most on, but we have a lot of other models also that are available in this framework. So this is a busy slide, but it's basically we can send data from PACS or research PACS, make it kind of safe, put it into this dashboard. We can have pre-trained models, ready trained models that we can put in as Dockers, or we can even train models from scratch inside the platform. So you can just, the researcher can come with, okay, I have 50 data sets. Can I just put them into your platform and just train it with a standard NN unit? And then you can kind of start to make a model that gets better and better over time. So this is kind of sounds like I'm a salesperson now, but I'm not. This is like different. Everything is called NEO. It's a bit confusing. So it's a segmentation tool. It's what's called NeoFlow, where you can set up pipelines with different processing steps that you can define. You know, you want to do some pre-process and some co-registration. After that, you want to put it into one model and output into another model, maybe. So you can set up this as like a graphical interface. NeoCowboy, a very strange name. So this is actually the part where you train and retrain your own models or the models that are already in the system, you know, so you can iteratively make them better. Analytics to show performance of a model over time, to get outputs of you know, segmentation, volumes, changes, etc., and also the number of models that are actually running, for instance, and reports that are sent either as PDFs to file or just back to PACS. So that's sort of that's the main framework of this NeoMantis platform. I think especially this segmentation tool is become very useful because it both enables segmentation from scratch for new data, but it also enables the radiologists to touch up results from model and make them better, so we can kind of iteratively improve model performance. And we can also improve or reject model output, so to flag those cases where the model doesn't do a good job. Okay, so that's quickly about our kind of endeavor to make commercial AI available for clinical use. We have, like you think, also have this approval from Director of Health to actually use this model on sensitive data. So that's useful. And we're in the final stages of having it approved by Sykehuspartner for proper clinical integration. Then, of course, we cannot ignore the fact that commercial solutions are here to stay. There are lots of them, and I know you do this as much as we. And it's easy to find arguments why we have to have commercial AI. It's, of course, the legal and regulatory requirements for MDR. We cannot ignore that. It's probably better integration into the RIS-PACS workflow. They have more capacity to be completely integrated into especially the RIS workflow, which HL7 compatibility. We can prefetch previous examinations. That type of integration is very hard for us, both because of resources and because of rights. They say sometimes they train a very large data sets. I'm not quite sure if that's always the case, and it's sometimes hard to find out what they're trained on. So I think we should take this with a bit of a caveat. The documentation for accuracy in large studies is also very variable, and I think you find meta-studies showing that a lot of these commercial tools are not really that well documented. And there may be less need for in-house expertise. But as I said in the previous counter slide, that may not be a good idea. So this, we have all started using these type of platform solutions. We have gone away from this. Every application has its own integration into the hospital. That's very inefficient, and it takes a lot of time because you have to risk assess everyone. Now we have 3 platform solutions in Helse Sør-Øst. I think you have the same thing here. So you have one platform that is approved by the hospital IT people, and then you can sort of subscribe to applications in this platform, and you don't have to do a risk assessment for everyone. So this is a good idea. So I think that's kind of the way it will go with all sorts of medical AI things. We have to have platforms to avoid too many approval rounds. We actually made a deal with Sectra before this Helse Sør-Øst came on board with their own solutions. We made a deal directly with Sectra to test out 4 applications. BoneView cure for BoneView for detection of fractures, Cure for brain leaks, ChestLeak for thorax, and Transpara. So far, we have only tested 2 of them, BoneView and Cure. They're running as we speak. I won't say more about this because Caroline will say this. The Cure is the one we're testing out. I know that Bergen is also interested in city captured AI solutions, so I guess that will be something to discuss. And then, of course, there is a big activity in Helse Sør-Øst. They're kind of very forward-leaning about the greatness of AI in clinical practice. And I think what we see so far that those that profit from AI in radiology are not maybe those that we think will profit from it. I will not say more about that now, but if you look at Helse Sør-Øst, I'm not sure if I'm allowed to show this even. It's a very ambitious plan for the different hospitals to introduce a lot of new AI solutions, especially Vestre Viken, which were early out. They have a very ambitious plan with new solutions. So I think we will see like this wave of AI solutions coming into clinical practice over the next 2 to 3 years. The big question is when will we dare to have autonomous solutions where we'll actually take the radiologist out of the loop. That's been discussed at these meetings we have in Helse Sør-Øst, but I think we're not quite there yet. Finally, I think it's interesting to see also because I have these discussions with my boss all the time, what's happening with AI? Why don't we see any real value of it in our hospital? We're spending money. Where is the saving? And I just saw this article from the New York Times last week from Mayo Clinic, and they're actually implementing a lot of in-house AI solutions. They're doing it like, I don't know, they can probably do it. But I also noticed that they have 40 people working on the development. So I could show this to my boss also. I said, we have 4. Can we have another 36? Yeah. So you've seen this. Even Geoffrey Hinton has now had to kind of change his statement from 2018. Then he said we can just throw away the radiology training because it's going to be taken over AI. Now he has kind of moderated himself and saying, like the people at Mayo saying that there will be this symbiosis between AI and radiology. We cannot make this work without experts to both guide and look at the results in a meaningful human way. So that's it. Just 2 words finally about this application that we have written together. I think this is really exciting times because we are in on this together, this big AIM Health application for the entire Norway, where we have very ambitious aims with Bergen, Oslo, Trondheim, Tromsø, all on board. We have some very good people involved, and this has been a lot of work. We will know on the 10th or 11th of June whether we get the money. We have applied for 200 million with a total budget of, I think, 360 million, something like that. So I think if we get this, that will give us a huge opportunity to actually do something at the national level. Of course, it's not certain we will get it, but we made it to the final at least. Okay, that's it. I don't think I will say this because it's fairly obvious. It's basically what I've said, more or less. And I just finally, I think this is so funny because when I'm very strongly of the opinion that software engineers is a new profession that needs to be in the hospital. And every time I hire one, I look at all the different professions I can have. And as I said, there is no software engineer, there's no programvareutvikler. We have vi har dyrepasser, dyrepleier, foredragsholder. And every time, no, this is such for engineers. Oh, sorry, we don't have it. So I have, this is from Aftenposten. We need to ansette som noen som gode PDB. I think I'm really having this strong kind of voice inside that we have to acknowledge software engineering has a very important new group of people that will be important for AI and for the future of how we run hospitals. Thank you.
So then please thank Caroline Skoge. It will be a really interesting. Yeah. So you are a neuroradiologist, and you have been actually working both with the development of AI tools and implementation in clinical workflow. So it will be interesting to hear about your experiences.
Yes, and again, thank you for the invite, and thank you for Atle for introducing all this. That means my presentation can be shortened a little bit. So I've basically, if I just go back, we've had both an in-house and a commercial tool that we have tried to, or that we have implemented. So I'll tell you a little bit about how that journey has been. But as Atle say, there's a lot of AI tools that we can buy commercially. And these were gone through, they went through about 100 of them, this paper. And just to show you, so these are the 100 they went through. And I just want to kind of show you where the AI, the commercial ones, where they come in. And it's in breast, chest, musculoskeletal, and neuro. And that's because these areas are the kind of the easiest areas to do stuff, because it's the big workhorse of the hospitals, and it's the where there's a lot of scans. So just looking at neuro, all we do is MRI and CT. We don't do anything else, right? So we stand for then 62% of them. Obviously, there's other ones. And then if you look at subspecialty, we have 38% of these 100 commercial tools. And these are the things with quantification, detection, and diagnosis, which is 82. So if you're looking at my special thing, it's, for AI, for the bleeds, the brain bleeds, it accounts for 82. And this is also an interesting graph. This is from Netherlands. They looked at how on calls, so basically from 4 o'clock in the evening till 8 o'clock in the morning, they looked at how this amount of scans have increased within 15 years, from 2006 to 2020 or 2020. And there's been a steady increase in all of them. However, if you look at this one, that is CT heads. And this orange line, that's trauma CT head. So there's been an actual extreme increase in just normal CT heads for some reason. And we're seeing that all around, like everybody reports this. And just to show you, these are 30 days from my list that I work on. So 30 days, we do 3,000 scans. And of those 3,000, we have about 2,000 CTs. And, in neuro, MRI is what tells us anything, right? CT is just to kind of shuffle along to make sure there's no bleed. But still, it's 2/3. Obviously, there's angios and stuff in there too, but that's 2/3 of our workflow. So I'm slowly getting to the point here. Sorry. So the clinical implementation. So back in 2016, I was so frustrated with the amount of CTs they do at Legevakt. At Legevakt, they're the only place in the whole of Norway that has their own CT scanner. Now they have 2 CT scanners, and they don't need to talk to a radiologist or anything. They actually just order a scan. They order and they get, and then we sit with the result and we sit and have to read it. And as of now, it's 6,000 head CTs, just head. I'm not looking at neck and face, but they've 6,000. Back in 2016, when I was frustrated, it was 4,000. So, and I just want to emphasize as well, they haven't increased the amount, like there's not that many people that have moved to Oslo in that period of time, enough for it to go up that much. There's only 5% of them that are positive. So there's so many negative scans, which is in the lower aspect of what the literature says, that they roughly around 8% in other institutions. But the funny thing, you would expect the 5% to go down with an increase in scans, right? Kind of thinking about it mathematically, but it hasn't. So what's the difference? So they've done 2,000 more scans. The only thing that has changed?
Electric scooters.
No, they got a new, maybe, or they got a new CT scanner. So they got a new scanner. So what I think maybe is that the electric scooters might have something to do with it as well. But I think that we're actually detecting more bleeds. We're seeing more of these tiny, some of the bleeds we detect are so small. They're so small and so insignificant, for at least for a radiologist. I don't know, the patient probably doesn't think so. So anyways, I went with this problem to poor Atle, and I was like, what do we do? And Atle's like, well, let's not find up the wheel. There's so many wheels out there. There's so many AI tools. So he got on the case to get the AI tools. But then we decided as well that maybe, how hard is it to build this wheel? So we also started then to look at the Barnehage, as you've seen. I went up there with Atle and all the other nerds, if you can say it. And we started chatting. And it turned out that these 2 bright guys, they had already thought of this before me, but they had thought of it on stroke. And they had the patients. They had started making the code. They had gotten some data from the RSNA challenge from back before. So they had already made my tool. So I was like, okay, can we steer it more towards trauma? Can I give you more trauma cases? And they're like, sure, give us trauma cases. So then I got these 2 poor listleggers to sit down and start drawing. And so they drew and drew and drew and drew about, I think it was about 200 bleeds for Brian and Bradley to work their magic. And they did. So then we made Viola 2.0. And we're like, yes, and Brian did this on his computer, and it was like, it's pretty good now. Maybe we can try it out. We'll try it out clinically. And I was like, okay, but it's important that the sensitivity is really, really high. And he was like, yes, very high sensitivity. And so now we have the detection. So it went from kind of just volumetric to now we have the detection and the volume. And this was my wish list, by the way. So this was what I wanted from him. But we're at the top at the moment. I'm on overlegger permission at the moment. So we're working on these next ones here and to get that as well. I might go past my overlegger permission, but and we have, and Neomensis, Atle went through this very good, right? So it's basically, we could sit and we could touch up all of the scans that they did. And so from the ones we've gotten clinically, we've touched up and we've sent them back to Brian, which I get back to. And obviously this is Neomensis, and this was the workflow. So unfortunately at this moment, it's not up and running, but it will be soon. But at this time, we physically had to push it from PACS. So that was one thing, which whenever you tell a radiologist you have to do something, they don't like it, right? So they needed to click 4 times to get this result. And they're very reluctant. But that's the only way we could do it at the time. But so you pushed it from Pax into this Neomedsis. This was the back end of Neomedsis. It went into the pipeline of Viola, and then it came back. 2, 3, it came back to Pax with either a nothing detected. Initially, this just shows a bit of difference between the developers and the clinicians, because initially it came back as pew, nothing found. And I went to the Neomedsis guys and I was like, what does pew mean? And he was just like, oh, it's like pew, pew, there's nothing found. And I was like, but this goes back into our clinical Pax. We can't have that. And he's like, oh, okay. And so we sat for a whole lunch, like after lunch, and we sat and we figured, okay, what about like a green brain? And then it's like, we need something green to say that there's nothing there. And so we came up with this green dot. So that was the story of the green dot that came. But if there's something detected, then we have the mask, and it says then the amount or the volume of the mask. So within the 3 months that we had it up and running, we had about 2,000 scans. And again, as you see from Legevakt, it was 5%. And this is the spread of the bleeds. During that time, remember in the beginning, I told Brian, I was like, I need a high sensitivity. We can't miss any bleeds, right? And he was just like, yes, lots of sensitivity. Yes, we got the sensitivity. But what do you think my colleagues thought when we had a specificity of 51? So they're like, what's the use of this? Like half of them come back as positive. I mean, this is a lot of work. So I was like, okay, we'll fix it. Went back to Brian and I was like, Brian, we have to have the specificity up. And he's like, yes, specificity, great. He gave me specificity, but then the sensitivity goes down, right? So you were kind of playing here. So then it was just like, okay, what do we do? Brian needs more scans. So we're giving him more scans at the moment. And since we don't have it actually up and running just yet, the connection between Neomedsis and Pax at the moment, this shows kind of the development of the Viola. So from the Viola 3, he got more scans from us. He got the scans that the initial Viola 2 missed. So he's been training it and doing his magic on it. And from what is on his kind of computer and with data sets from the outside and stuff, he claims now that he's up on a sensitivity of 90 and a specificity of roughly 90. So we're very much looking forward to trying that out, which we're hoping to do very soon. So then eventually Atle managed with, he lost a lot of hair, I think, during that process. Yeah. Poor guy. Eventually we got cure about a year or two later, something like that. And obviously it looks, there's no pew, there's no big green ball. It looks very sophisticated. It's very nice. It comes in our workflow list, which we couldn't because Sectra wouldn't do that for us. But so it comes back like this. So it looks quite nice, right? At least when you get used to it. So you have critical where they found something, and then routine where they couldn't find anything, or where cure doesn't find anything. It only takes about 2 to 3 minutes. And then it has the actual findings and this amount of the bleed, and it also does fractures as well. So it was great. And they promised us a good sensitivity and specificity. So we were like, yes, this is great. So you can see here, it does basically the same, like it outlines the bleed, and it does give a classification, but it doesn't say what it is on the scan. So it basically says here, intracranial hemorrhage, and it says that you have a parenchymal and a ventricular hemorrhage, and there's a mass effect. up like this, you have the mask on that picture, and you get a report. So the report actually just comes up in the window for us, but you can't integrate the report, or I guess you can eventually if you want to integrate it into that it can go into DIPS, but we haven't let that go just yet before we've tested it out. It looks like this. And initially in the shadow mode, it did great. So shadow mode meant that we could see the results. So that, you know, the first where you saw the critical and the routine, we could see that. So we could see where it said it was positive. And so we're like, okay, this is really good. You know, it's 95% because we even checked it up against the radiologist and 84. Wonderful. And then we got the masks. So then we went live. And for some reason, it plummets. It just crashes. So we're down and it's steady. We've done it now for about 3 months and it's steady. It's about 80% sensitivity and 80% specificity. And we think the reason, we learned a new word, accidental positives, which means that basically the Cure says that there is a bleed, but it's highlighting the wrong bleed. So it's not finding the actual bleed, it's finding something else that's not a bleed. So we're still working. So now we have that data set. So we're going to run that through Viola 3, and we're going to see, kind of compare how it actually performs. But we are quite disappointed with Cure. We thought it would be better. And obviously we have our listens that are amazing, especially with specificity. But they do take a little bit longer, from 3 to 5 hours, whereas the Viola and Cure, you know, it's instant, it's there. We always find this, I always love showing these slides. So these are the false negatives, right? This is what it can't pick up. They're small bleeds. They're not going to be, it's not the critical bleeds that's actually going to kill a patient. So it's just these tiny, tiny bleeds that, for me anyways, are insignificant, but not maybe for the treating physician. And then we have the false positives. Now, the great thing, which I'll show you just in a while, but the great thing about Viola, we know on the scans we've given Viola, we know all of the scans, so we know where it goes wrong. Like, we know, it's like, oh yeah, that makes sense because we've given you some scans of that. Here, we don't know. We don't understand these false positives. We don't, like, okay, maybe there's some calcifications. Okay, that's okay in the basal ganglia. But this one, why? Why does it think it's a bleed there? Right? There's nothing, there's no reason there should be a bleed there. And the same thing here. Maybe it's an artifact. It's all the way up in the front there. It's an artifact, maybe, but why? So that's the bleed, but it doesn't take the meningioma that's there. Maybe, but it's probably not trained to. But it doesn't detect this small chronic subdural, and obviously this is the fallback. It doesn't do the chronic subdurals, which that none of them really can do. And then this one as well, like, it managed to get this bleed, which we were quite like, it's like, okay. But then we have to do the control. So we do the 6-hour control. So it doesn't detect that bleed again. But then it decides that the veins up here, it's like, oh, there's a bleed. So, but it didn't do that on this initial scan. So it's like we don't know. Whereas with Viola, we kind of understand a bit more why it does the bleeds, which is what we get to here. You know, so we fed Viola a lot of the parafalcine SAH, yeah. Anyways, alcohol, and around the paraplantory and along the veins, because those are hard bleeds, and it's good that it detects this, because then we can go like, oh, I don't think this is a bleed, you know, because it gives you focus, and it's like, oh yeah, no, it's just the angle, and it's not. I don't think that's a bleed. The false negatives, again, they're small. I'll help you a little bit, maybe. So here they are. Now this one in the thalamus there, like why it didn't detect that, we have no idea. So that's a down. But again, we segmented it and we put it into Brian's new model. So hopefully that won't happen again. But again, these other bleeds, they're small. They don't do much damage to the patient, I think. And then I had the difficulty getting my colleagues to push these pictures, right? And they're like, oh, I don't want to do AI, it's stupid. It's only positive, so I'm not going to send it. And we're like, okay. But then when we went through it, we're like, okay, there was reported negative, but Viola says it's positive. And when you look in all the planes, it is positive. So then we have a radiologist, and we found this bleed about 2 weeks later. So it's kind of like, what do you do then? So then it was kind of like a big calling the neurosurgeon, and the poor patient had to lose their license because they'd had a bleed. So so I think AI and radiology may be best, even though some papers say not. But another downfall. I don't think you need to be a neuroradiologist to see something's wrong. Anybody there? There's something big there, right? If we give a little contrast and do an MRI, we see there's definitely something wrong. Now Viola decided this was wrong. This tiny, tiny little dot, right? Because we haven't given it. This is not what we've trained it to see. We haven't trained it to detect tumors. We don't detect tumors on CTs, This is because they're so rare. But again, we have the possibility because we have control over the code. So I can probably eventually go back to Brian and say, listen, I have some tumors too. But again, you need to know what it's good at and what it's not good at. So we're at the moment, we've detected, we've quantified, and hopefully we're going to be able to give a proper diagnosis eventually with classification of these bleeds. The clinical value, that's always what is asked, right? Where they're always asked, what's the clinical values? Is it just a fun tool for you guys, or is it actually anything of use? We've looked through it, obviously prioritizing where you can get the critical, the routine that Cure has helps you because you actually go to the critical first. Reduce the workload. This is what I want to happen is that the listläges, that they don't have to look at the negative scans on call, that only one radiologist needs to look at the negative or neuroradiologist, that they just sign it off. And then you get the immediate report that maybe eventually that the treating physician can actually act upon the report, that if it says it's negative at Legevakt, the patient's drunk, just get out of here. We don't need to wait for 35 minutes. And you get it's more rewarding, isn't it, to say it's this many mils of bleed rather than just giving lots of different measurements in all different directions. So we still think that AI radiologist is best. We're hoping to kind of make this into a structured loop. It's a little bit into the future, but hopefully at Legevakt, that we can, what they have with Gleamer that we've heard from Västerviken. Kind of went through this, but I think that the most important thing is the actual direct communication. We're sitting there discussing about this green ball. We're sitting there discussing, I can go back to Brian and say, listen, it's missing a lot of these bleeds. I'll give you more of those. How many of those bleeds do you need for it to be able to detect it? So you can sit there and have that direct communication. It's wonderful. Free can be discussed, but we definitely do feel an ownership to it. So if we've found up the wheel, I don't know, we're still working, trying to. So thank you.